welcome to another video. Today, I'll be exploring a specific scenario. So, what is this scenario? Well, I want to solve for the temperature of a flame coming from a burner. So, to sort of draw it out here, I want to solve for this temperature here. And so, there will be sort of a bunch of assumptions that we will have to make here to make it possible to sort of solve for it, at least on my level. And so, what are these assumptions? Well, firstly, let's assume that the burner here is super high tech, and because of its high tech-iness, it's adiabatic, uh, and so there's no heat losses. So I'll put that here. Adiabatic, so Q equals 0. And secondly, there is no non-flow work, so that is equal to 0. There's no whatever, blending, stirring, pump, that type of stuff. None of that. Secondly, whatever kinetics that are happening will be totally ignored, or at least the effects of such are so tiny that it's negligible. So kinetic energy will be equal to 0. And that same sort of thinking is applied to potential energy as well. That will be also equal to 0. And then we're also assuming that the system that we're working with is at steady state. So anything with respect to time will be equal to 0. I'll just use X to label anything. And so what are we given exactly for the scenario? Well, we're given that the type of fuel that is going into this burner is natural gas and air. And so natural gas and air. And so I am given two sort of specific compositions here. For natural gas, it'll be methane, ethane, and propane. And as you can see on screen, that has been on screen for a while now, I am also given specific mole percentages of them too, with methane being the most at 95%, and then ethane at 4, and then propane at 1. And while it's not stated on screen right now, the um, air composition that we'll be working with isn't exactly the one that you would encounter in real life, because the 1% argon will be just considered nitrogen, just for simplicity. And so, like I said, the air composition is 79 to 21 nitrogen to oxygen. All right, and so that's sort of all we're given at the start here. And so the first thing that you comes to mind to solving for temperature is sort of an energy balance equation, right? And with all the assumptions that we've made earlier, it really does simplify it down a whole bunch, since a lot of the terms that we will be needing is 0. So to start off with, the changes to internal energy will be 0 because it's steady state. Kinetic energy, potential energy, non-flow work are all 0, as stated here. Adiabatic, 0. So all we're left with is the enthalpy going in with whatever small amount of mass is going in, minus the enthalpy going out with whatever small amount of mass that's going out. And so just judging from that equation, it basically is the total enthalpy going in is equal to the total enthalpy going out. And with seeing this, we can sort of see that whatever is happening inside of this, there's a temperature increase to compensate to make the enthalpies equal. And so where do we go from here? Well, um, there we have to sort of see that for a burner to even work, there is a combustion reaction going on, right? And so we can sort of write out the combustion reactions that are occurring inside this burner. So to demonstrate, to just sort of write one out, uh, we'll do methane here. So CH4 reacted with oxygen, and that creates carbon dioxide and water. And so we also have to balance this equation, right? And so the coefficient here is determined by the amount of carbons here, so that's 1. And the amount of the coefficient here is determined by the amount of hydrogens here, and that's 2. And we're also, this oxygen coefficient is determined by the amount of oxygens over here. There's 4, so there's 2. And so we're missing something. We're not reacting with pure oxygen, right? We're doing it with air. And so we have to account for the nitrogen that's also coming in as well. And like I said earlier, that's coming in with a 79:21 ratio. And because there's 2 oxygens over here, there also has to be 2 over here. And so you might have noticed when I was writing it earlier, nitrogen isn't actually part of this combustion reaction. It's just the oxygen that's being reacted. So the fact that we're using air, it sort of lowers our overall flame temperature in the long run because we have to sort of heat the nitrogen that's coming in with it. And like I said earlier, it doesn't get reacted, so the same amount of nitrogen comes out as well as a product. And so we can sort of do the same thing here for ethane, which it won't be too different. Uh, we'll just have different coefficients. Right? So this is determined from the amount of carbons here, here, 4, 7, so that has to be divided by 2. And nitrogen gets the same coefficient as well. And so where do we go from here? Um, so one thing that we have to notice here is that to sort of create all of these compounds, there's an enthalpy of formation to them, right? Each compound here has a sort of specific enthalpy of formation. And that's how we'll connect it to the energy balance equation here. And just thinking about that for a quick second, since enthalpy of formation is based on a per mole basis here, changing any of these coefficients within the combustion reaction will ultimately increase the enthalpy that's being accounted for. And like I said earlier, the temperature is increasing to make sure that the enthalpies, the enthalpy in and enthalpy out equal each other. That will obviously sort of change everything. So we can sort of say that this whole scenario, the temperature in the long run is dependent on whatever coefficients are being placed on to these compounds within the combustion reaction. And so now that we've sort of made that link, we can sort of start making our equation to solve. And so let's do that in the next part. All right, so now that we've sort of connected the enthalpies from the reaction to the equation, we still aren't sure how temperature is sort of being played with all of this. And so let's start digging into that. So if we were to look up the enthalpy of formation for some of those compounds within those reactions, we'll get a certain value. But with that certain value is tied with a certain temperature. In this case, it'll probably come up as standard state, so 298 Kelvin. But if you were to try to look it up at a much higher temperature, you'll see that its enthalpy of formation value is actually different. And that's because it depends on temperature. And so that's sort of where we'll be going on from here. So if we write the equation uh, for changes in enthalpy here, we get uh, changes in enthalpy with respect to temperature here at a constant pressure with changes in temperature. This is what we get. And of course, since we're dealing with ideal gases, the second term is gone. And so this term right here is most commonly known as the heat capacity at a constant pressure. And so, like I said, changes in enthalpy here is equal to this heat capacity times the changes in temperature. And uh, with what I said earlier, if we looked it up at a larger temperature, the heat capacity value would be different. In most cases, if your temperature range is small enough, you can use sorry about that, a constant CP value, and it wouldn't affect that much. But in our case, where the temperature range is very large, CP will be changing along with temperature. And so how do we sort of calculate something that's changing with some other variable? Well, that's easy. Integration, right? That's what it was made for. And so that's exactly what we'll be doing. We'll be integrating these. Well, maybe not this. We'll be integrating this left side here, right side. And so what we get is that the changes in enthalpy here are equal to the integration of the changes in enthalpy at some beginning temperature and some second temperature, which is equal to the integration of the heat capacity at constant pressure uh, dt. And this is obviously from T1 to T2, temperature 1 to the second temperature. And with that, for here, just so that it matches along mathematically, there will be some corresponding enthalpy value at that first temperature and some corresponding enthalpy value at that second temperature. And we see how it works out here. But what we don't know is how CP depends on T. We can't sort of integrate this the way it is right now. And so how does this depend on temperature? Well, if you look on screen, it depends via ChemCAD's equation 107, this right here, what I'm circling. Y being the heat capacity value, and this equation here showing how it's dependent on T, on temperature. And so that's what we'll be integrating here. And so I have done that already to save some time here. And what we get is this equation here. Note that I had to switch the E's from equation 107 to F's only because Wolfram was considering my E as exponential. So to make sure that it didn't do that, I swapped the letter. And so this is the equation that we'll be using here to calculate that enthalpy change. And so now that we have our equation, we can move on to coding it all out and solving for our final temperature, which we'll do in this next part. All right, so here we are in the coding portion, in which we'll use everything that we've sort of discussed so far to solve for the temperature, right? And so I have brought in our usual imports here, uh, along one of those, including the chemical database that we'll be using to sort of get our properties from, and the coefficients for the equation from ChemCAD from before, right? And so first things first, what do we want? Well, let's pull our properties, right, for all the compounds that we'll be using. And so I'll just be putting it into variable p here, and it'll be from CHE, which is the repository, and props. And so what compounds are we using? Firstly, methane, then ethane, then and propane. Next is oxygen. Then we have nitrogen. And then we have carbon dioxide, which I forgot to put in. Carbon dioxide. And lastly, water. All right. And so now, if we wanted to view any of those properties, you guys can see on the list here, I'm pointing towards it, but you can't see my hands. But let's say that we wanted the heat of formation for an ideal gas of these properties, and we get those values. And you can note that the oxygen and nitrogen ones are 0. Because they're in their elementary forms at that's what they're most plentiful at. All right, so what do we do from here? Well, we went through all that trouble to make a function for the integrated specific heat, right? And with that, we'll be able to calculate the enthalpies, enthalpy change at any temperature. And so let's put that in as a function. Integrated CP, that's what I'll call it. And it'll get a temperature inputs. And so let's transfer that over. And so I have the equation here. Don't forget so we can see the coefficients here for A, B, C, D, E for this equation. They are stored in this database. So all I have to do is call them. So A, right, times the temperature plus I will speed this up. I will copy this. B times C divided by, this is cotangent, hyperbolic cotangent, which is the reciprocal of hyperbolic tangent, C over T. Make sure this is correct, right? And this is being subtracted by, and I'll put this in another set of parentheses so that nothing funky happens. Next, we have D and E. Remember, I only used F because E wasn't working correctly. So D times E. And then that is also being multiplied by hyperbolic tangent. E over T. All right. And just to show the properties here, I'll open it up for ethane. So the heat of formation is right there, which is that value there. And you can see that it auto converts to per mole instead of per kilomole. But that isn't the case for the heat capacities, as this is being still considered kilomole. So what we'll have to do here is to divide by 1,000, whatever value comes out of this. So I will do that. And that should be done. So now we have the integral, the function inside our thing. And so with that, like I said earlier, we can calculate the actual enthalpy at this higher temperature with the change in enthalpy here. And so as we have it right now, our T1 and T2 on that integral symbol is empty. And so as you know, we have to put in the difference to sort of get the correct value. And so what we start off with the heat of formation at standard state, right? And we are heating it up to some temperature, right? The T2 in our integral. And so we will add that. Kind of jumped the gun here. I didn't even name my function. The enthalpy, and the temperature will be inserted into that at whatever higher temperature we want. And remember, this is an integral, so we have to subtract by our starting value, which is 298.15. And so with this, we'll be able to get the enthalpy value at that higher temperature. And so now that we have that enthalpy value, where do we go from here? Well, like I said earlier, these enthalpies are sort of dependent on the stoichometry of the reaction, the combustion reactions, the moles of each specific compound. So what we do from here is to sort of input our stoichiometry, our moles of each compound, so that we get the correct enthalpy values. And so let's do that. So as you could note, we were given our fuel in terms of percentages, mole percentage. And so those aren't exactly the actual correct number of moles. And so let me put them in first here. So we were given 95%, 4%, and 1%. And so what we need to do with that is we need to extract the correct number of carbons and hydrogens that are actually coming in with that, the correct number of moles of each of those elements coming in from the fuel. And the only way we can do that is to do a matrix multiplication of the fuel with the each compound's molecular formula. And so let's do that. So let's do fuel CH is equal to, this is methane, 1 carbon, 4 hydrogens. This is ethane, 2 carbons, 6 hydrogens. And this is propane, 3 carbons, 8 hydrogens. And like I said, we want to do a matrix multiplication for the correct number of carbons and hydrogens, moles that is actually coming in. And so let's do NC and NH, moles of carbon and moles of hydrogen will equal the matrix multiplication of these two arrays. Almost forgot. NP dot array. All right, and so as we can see here, this is our actual total moles of carbon, 1.06, which sort of makes sense as our highest percentage of a compound is methane, right? And that only has 1 carbon. Well, yeah, plus the other small percentages of the 2 and 3, right? 95% of 1, and then 4% of 2, and 1% of 3. And we can assume that's correct for moles of hydrogen too. So now that we have our natural gas, our fuel done, that portion done, we need to sort of calculate all the moles for the other stuff within the reaction, right? So carbon dioxide, water, the oxygen, the nitrogen. And so, like I stated earlier in the video, the amount of carbon dioxides are determined by the coefficient, or I mean the subscript on that carbon within the natural gas. And so the moles of CO2 is equal to the number of carbons. And then for the water, H2O, that is equal to the amount of hydrogens coming in from the natural gas divided by 2. That subscript divided by 2. So number of hydrogens divided by 2. Moles of oxygen is equal to the summation of those products, right? So CO2 plus H2O divided by 2, since H2O is only actually bringing in one oxygen. And to sort of prove that this is correct, right? At least this calculation for oxygen, because during lecture I had a hard time grasping it, but now if we were to use the combustion reaction with methane, for example, the amount of CO2s is equal to 1, because there's only one carbon from methane. There are 2 hydrogens coming from, 2 waters, I mean, coming from the 4 hydrogens for methane, right? And so we need 2 O2s, so to say. And so carbon dioxide is equal to 1. Hydrogen, the water, I mean, is equal to 2. Divided by 2 is 1. 1 plus 1 is 2. So that gives us the correct coefficient there. We're sort of making it so that this is doing the balancing for us, so to say. And then nitrogen, super easy. That's just a ratio of the oxygen coming in. So O2 NO2. All right, so we have finished calculating balancing all our moles within these reactions. And so now we can sort of go along and multiply our enthalpies with these moles. And so let's do that. So to sort of clarify what we're doing here and what I said before on how we'll be multiplying the moles and enthalpy here, our ultimate goal is to set the total enthalpy going in equal to the total enthalpy going out, make sure those two are equal, and the temperature must change to make sure that's equal, right? And so in order to achieve that, we need to find the total enthalpies going in and out. And that's why we had to find the moles of everything for the reactions, because those are the moles that are coming in. And with those, the enthalpies of all those moles, right? And so that's what we'll be doing here. We'll be sort of constructing an array or list with respect to this list. So it will have to be in the same order here of all the stuff, of all the moles that are coming in. And then we'll have to do that for all the moles that are coming out as well. And so let's do that, right? So moles in here. And because we have a array already for the fuel, which covers the methane, ethane, and propane, we'll have to do some concatenating. So it'll be the fuel with the array here of next the oxygen, right? NO2, then the nitrogen, and we have no carbon dioxide and water coming in. And now, like I said, we'll do the same for the outs, but this time we don't have to do any concatenating. It will simply be 0 methane, 0 ethane, 0 propane, uh, 0 oxygen. The nitrogen will be coming out, and the carbon dioxide. Oh my gosh. And the water. H2O. And I forgot to put the brackets. All right. And so now we have our total moles going in and total moles coming out. And now all we have to do now is to find the total enthalpies that are that are coming that are a result of these moles coming in and out. And so to do that, um, we need to do a dot product, right? So that the moles multiply with their respective enthalpy value, and then it gets summed up all in the end, because that's what the dot product is. So let's do that, right? So let's find the total enthalpy going out, right? So like I said before, we'll have to do a dot product where each of these values is being multiplied with their correct uh, other value in that list, right? So the first value will be multiplied with the other first value in that list, and then it will all get summed up. And so you see how this is why we had to make sure it is in respect with the same lists, because this is in respect with that list, right? And so the dot function, the dot product is just called np dot dot dot. Um, and so it will be the enthalpy function at whatever temperature, right? With uh, the stream, the moles of going out. And so this won't give us a value because T isn't defined right now. But let's say that T is equal to 2000. That is our total enthalpy going out. And so if we did the dot product of the enthalpy going in, which is at standard state, right, with the moles going in, we have to now adjust this temperature value so that these two values are equal. That's what the energy balance equation says, right? These two have to be equal. And so instead of manually sort of adjusting our temperature, we can use a root solver to ultimately do it for us. And so that's what we'll do. So I will just, I'll name it just equation. And root solver requires a vector as an input. So we'll have to unpack our actual temperature value from this, as it will probably be the only value in there. And to zero it out, we need to find the difference of the two, right? So I will do that. Crap. uh, don't worry about that on screen. And so we can get rid of these now. And oh, also would have been very wrong there. We need to return this as a array because that's how root sends out the result. And so now we can use the root equation now with our equation. And we need to supply it some guess. We can simply do 1000, maybe. Doesn't really matter. And enter. And this is the value that we get for our temperature. This is the temperature of the flame here, 2332 Kelvin. So if we wanted just that value, we can do this, and we'll get it back as an actual scalar value. And so that opens up a lot of things that we can do. We sort of created a general coding here that we can sort of adjust things as well. And one of the things that we can adjust is, like I said, way earlier in the video, this thing is dependent on the coefficients. And so if we wanted to sort of change one of those, let's say uh, we want excess air, for example, just because in a real life scenario, right? Not that this is too realistic. Um, there isn't perfect mixing sometimes, and because of that, pollutants like soot could form from the combustion reaction because of high concentrated areas of the natural gas, and yeah, just because of the high concentration of natural gas that's coming through. And so to sort of fix that, we can put in excess air, right? And so we'll be adjusting the coefficients here a little bit. And so let's say we wanted to simulate this scenario. So we want to put in excess air, which I'll just label as excess air. And let's say we want 20% excess air. And so what we'll have to do here is adjust our coefficients, our moles here, right? And it's pretty simple. We'll just have to make sure we add it to the moles here. So that's 120%. So plus 1 point excess air. Not plus, times 120%. So then that'll give us 20% extra air. And with that, it will also change the moles down here. This will be accounted for, but we have to, the oxygen here, not 20% of it won't be reacted, right? So times the excess air, right? And N2 will change accordingly with that because it's based on oxygen anyway. And the reason I didn't change it here is because this is the 120% value. And so now that we've sort of made those adjustments, if we were to run this now, you can notice that it's at a lower temperature. And that's because that extra heat that we had to put in, that temperature loss is accounted for trying to heat the extra amount of air that's coming in. And so if we really wanted to try to get a super high temperature, obviously we wouldn't use just plain old air. We would use pure oxygen, which would make it the sole thing that's combusting, right? That's the only thing that's needed to combust. And so then we wouldn't have to lose some of the energy that's being required to use to heat up the nitrogen. And obviously then we would get a much higher temperature. And to sort of prove that, I can comment out this nitrogen and add in a new nitrogen number, because everything here is, make it 0, right? And just, we can see that we get a extremely higher temperature, a little bit lower than what it would be because of the excess oxygen. But yeah, and so that's how we solve the temperature for an adiabatic flame, obviously with a bunch of assumptions made. But yeah, this is how it's done.